started the recording, which means. But yeah, welcome everyone to this. And that's my biomartial duty obliged me to do. I will totally go on. Yeah, so our speaker today is Alessandro Lonardi, who is a postdoc of our own, working with Christian. And I think you told me this is mostly about the PhD work you've done.
Yeah,
before, that you're going to present here. So yeah, very much looking forward to it. It'll be about message passing on hypergraphs.
Okay, thank you. Okay, thank you for having me, everyone. So yeah, today I'm going to be talking about one work that I did during my PhD related to message passing on hypergraphs, detectability, face sensitivity, and higher order information. Okay, so the work that I'm going to be presenting today, it's also a paper with the same name that is published in JSTAT. You can check it out. Also, if you have a phone, you can scan the QR code. It should be working. Otherwise, I'm gonna leave some links and identifiers that you can copy. And then, yeah, also I'm gonna self-host all the slides in a website posted at the end if you want to check the slides afterwards. Okay, so the topic today deals with there are three main keywords that you should at least understand or be comfortable about. One is hypergraphs. One is community detection, the other one is message passing. So I'm gonna pretty much introduce this concept from the very basics. And then there's also a bit of a warning. So the paper linked to this presentation is a rather technical paper. So today I'm gonna be giving I think a rather not technical, but I'm gonna give a more introductory presentation on the paper. And the goal, I guess, is to understand the problem, the challenges to solve the problem that I'm going to present in the result. That may be also a general sort of schedule for all presentations, but especially for this one. And then there are some slides where there's some difficult content, meaning a bit more nuanced, that I'm going to skip through a bit, and they are marked with the red dot. Okay, so first thing is, what is a hypergraph? So graphs and hypergraphs are two different objects. This is because this is something that pops up sometimes during reviews, especially. And if you want the reason for this, so what is a graph? A graph is a mathematical object comprising of nodes and edges, right? So the edges connect the nodes, and the hypergraph is a generalization, if you want, of this graph, where edges are substituted, or what they're called hyperedges, that contain a set of nodes, right? So this that you see here would be a hyperedge of dimension 3, for example, with 3 nodes inside. And if you want a more a technical argument of why they are different objects, is that a hypergraph induces what is called a unique click decomposition, but the converse is not true. So what is a click decomposition? So if you take this hypergraph, and for every node within a hyperedge, you draw an edge, so what you see here on the left, and do the same up here. So this is exactly the click decomposition of this graph. So you project the hyperedges into edges. So for every pair of nodes within the hyperedge, you just draw an edge. And if you want more of qualitative intuition, think about sending a message into a group chat on WhatsApp versus sending to each person in a group chat message, and think about the effort that it takes to do it. And the more serious intuition, think about how misinformation can spread, for example, in graphs and hypergraphs because of that. If you want plenty of other reasons, here I link one review that gives you a lot of problems, percolation, synchronization, and whatnot that relate to hypergraphs, especially.
Can you explain this again? So the clique is defined how?
So a clique, you just take every hyperedge, and for every pair of nodes within the hyperedge, you just throw an edge.
The hyperedge is, where does it come from?
The hyperedge, you are given a graph, and given a graph, you can draw a clique. So you give a graph, hypergraph, sorry. It's this object here. You have hyperedges where you have a group of nodes that interact all together. So this represents sort of
additional information. So you
have exactly.
And you give additional information what nodes are somehow connected. And
exactly.
But they are not connected by edges.
Exactly. So these are only connected by a group interaction. So if I have to say something to you, I'm going to tell it inevitably to another person because we're only part of a group.
But even though the edge received that information, it doesn't have an edge.
Right? Exactly. So in this case, there can be also an overlap. So this node talk to this node via can talk similarly to this other node. and also decide to communicate with both nodes together, or can decide to talk singularly to this other node while not talking to this.
And these channels will then be distinguished whether they receive information via direct edge.
Exactly. Yeah, there are two options.
So now that we're getting technical, is the resulting graph on the left and the multi-graph when you double up the edges, or you just combine
No,
the extra edge from the
yeah,
hypergraph?
you can give them a weight. For example, you can draw a multigraph or you can draw a simple graph, just projecting it into one single edge. In this case, I'm not giving weight. Later on, I'm going to consider the case with weight for one single example. But yeah. Okay. So the second topic to introduce is community detection. What is community detection? At a very foundational level, you have, let's start with graphs, right? You have nodes connected by links, and you want to find a partition of the nodes. There is a coarse graining with respect to, that gives you a coarse grained information of what the graph says. For example, here you find some partition of nodes that tell you something about this graph here. Here you see that there are nodes in green that are the one with the highest degree. And here instead you have nodes that are tightly connected with each other from one community, what's called a community, and here they form another community. So and then all these possible partitions, they retrieve or they give you some information about the graph. So here I'm not defining specifically what the information is. So just to draw it pictorially, so these different partitions, say B1 is this partition, may give you this amount of information. This partition here, the one on the right hand side, may give you more information, and so on. So again, I'm defining it rather loosely because there are different challenges in community detection. Okay, and I just want us to get the gist of the problem. So one challenge is that ground truth communities in general are impossible to define. So if you have what's called a planted setup, where you synthetically create a graph and you assign to each node the community, then they're good to go. But in reality, if we all, let's say, chat to each other, and we are all part of a network, there are different ways to partition us. It could be because we work together. It could be because we have relationships outside of work, and so on and so forth. So in general, it is very hard to define ground truth community for real world networks. And then the other question is, how much does one partition, how much information does one partition give you? And that's also a very tricky question. So as I told you before, one partition could be more informative because it gives us intuition about the degree of the graph, another one because of the clustering of some community. In general, also the problem is a technical issue. There is exponential computational complexity. So given k classes and nodes, you have k to the n if you want to be very naive ways of partitioning the system. And yeah, so you need to be smart in the way you design your algorithm to solve these problems. And in general, there are different methods to solve these problems that fall in what's called a descriptive and inferential community detection. So descriptive community detection is you observe the graph, you observe some features of the graph, and you partition your communities based on some ad hoc observation. For example, the degree on the sortativity, as I was mentioning before. Inferential community detection is something a bit more nuanced, and it's exactly what message passing, so the method that I'm going to present, is about. So inferential community detection is related to a generative model. That means we have a set of rules, and we assume that this set of rules create your graph. Alice talks to Bob because they belong to the same community. So you give the community, and then you create the edges based on the community. And then inference is the process of recovering the communities once you observe the edges. This may be a bit fast, but I'm gonna give you a proper intuition of this later on, explaining all the steps.
Very quick check.
Yeah.
You're talking about static graphs, right?
Yeah.
There's nothing there.
Yeah. So there is also dynamic methods for doing all of this, but what I'm saying now is all for static graphs. Yeah. Okay. So message passing, for what we are concerned, is a method that performs inference. So you observe the graph and gives you a partition that is informative about the coarse-grained structure of the method. So if you want to know something about message passing, you should read this book. It's the Bible of message passing, belief propagation, and exceptional book. Okay, so again, what we want to do is to perform inference, so find the communities, and we want to use message passing. So here I see something a bit more details about message passing, and I write message passing perform inferences of what are called graphical models. Graphical models or also factor graph. So this is a bit more of a technicality, but what we're interested about is that message passing is a technique that allows you to recover the probability of belonging to a given community of a node. So it gives you the marginal probability of each node to belong to a certain community. And it does that on a mathematical structure that is called factor graph, okay? So this is rather technical, but what I want here to everyone to understand is that you have this method and you want to perform inference to compute the marginal probabilities of each node to belong to a community. And these marginal probabilities are going to be maximum likely estimated. Okay, so message passing is also efficient. So this takes away the burden that I introduced before. So it's a very fast method. So the exponential problem that you complexity that you had before becomes polynomial with message passing. Okay, so this introduction might have been a bit fast, but now because I'm going to give you step-by-step examples. So let's look at how inferential community detection, so message passing or more community detection works in practice. So you have this task. So you have a network, and first thing first, you sample the ground truth community. So here we're in this synthetic case. So you assign to every node a community. These are the oranges, these are the greens, these are the blues. And then you build a graph where two nodes, I and j, in class A and B, are connected. And this is the entrance of what's called an adjacency matrix. So it's 1 or 0. So it's a Bernoulli random variable that says to me two nodes are connected based on this probability PAB. So the core bit of this line here is that two nodes are connected based on a variable that depends on the classes of the nodes. So two nodes are likely to be connected if the probability their two classes are connected is high. Give you an example of this, it may be that mathematicians talk to engineers. So if I'm a mathematician and my friend is an engineer, and our two classes are likely to talk to each other, then it's likely that the two of us interact with each other. So it goes from a class level information, that's mathematicians and engineer have a high probability of talking to each other, and it samples a connection between each individual belonging to that class. So you sample the graph of communities and you build a graph like this. And this is what before I said, inferential community detection posits a generative model. This is called the generative model. So you have a model to build the graph. And then inference is the process of detecting the communities. So first you sample this, then you ignore the community classes, and inference is the inverse process. So you observe these connections, and you want to understand who are the engineers, who are the mathematicians, and who are the economists in this example. Okay, are there questions?
This is still for normal graphs.
This is still for normal graphs. It's just to build the intuition, and then I'm going to switch to hypergraph in 2 minutes. Okay, and there is a big result of a very seminal paper, as well, that tells you this. So when you build a graph, you can fine tune the way the nodes are connected together. You can have a graph that looks like this, that is called assortative, where the engineers have a lot of connections with each other, the mathematicians as well, and the economists as well. Or you can have a more mixed up situation where everyone talks to each other. And then you find out that if you, and these two situations are controlled by the in degree and the out degree, meaning the number of connections I have with people from the other classes. In this case, mathematicians have a lot of connections with mathematicians, but very little with engineers that are important to us, let's say. So in this case, once you have this scenario here on the left, so everyone is very tightly clustered together, so your links are very tightly clustered together, then it's very hard to recover all the classes. So the accuracy here is what's the fraction of classes that I've recovered. So you're very close to 1. And then the more you mix up the network, so you end up in the right hand side here in a situation like this, where everyone is mixed with each other, then the accuracy drops and you have this nice phase transition that happens experimentally. And message passing, so it's this red line, gives you allows you to recover efficiently this phase transition. You have a Carlo method, there are the blue dots. And then you have two states. One that is called detectable, when you recover the partitions, the communities, and the other is under.
Could we check?
Yeah.
Phase transition in the sense of if you make these graphs larger, this
Yeah.
transition becomes sharper and sharper.
Yeah, sorry, I put it here, and this is at end infinity. I just so this is for very large graphs you observe this. So experimentally here you have 500K nodes, I think. So yeah, so it's of course at n equal to infinity. So and then there is also very nice theoretical results. The expression itself doesn't really matter, but the thing is that you can find exactly what is the point where you have this. You can find the critical point where this phase transition happens. Okay, and yeah, this is it. Okay, so this was introductory, and now what about hypergraphs? So in general, then there are three questions that our paper talks about. And then the questions are related to to this main broader question, does a phase transition like the one I just shown to you appear also for hypergraphs? And if yes, what is the contribution of these hyperedges? So the fact that people or nodes communicate in these group interactions. And can we find this critical threshold also in closed form? That would be very nice. And then there's a third question that hopefully I will have the time to go through. That is, will the results tell us something about hypergraphs? Yeah. Okay.
I assume they do.
Yeah, the answer is yes. Otherwise, I would not be here. Okay, so let me start with the first two questions. So what is the contribution of hyperedges? So first of all, we have to define a generative model for hypergraphs, right? So again, inferential community detection is based on the idea that you have a procedure to create a graph, and then you reverse this procedure and you try to infer the community based on the observations that you have. That is the hypergraphs in this case. Okay, so what we did is that we generalized the stochastic block model. So it's this stochastic block model is the name of this generative process that I described. So two nodes are interacting based on a probability matrix, or it's called also affinity matrix, that their two classes are likely to interact. And then we build the hypergraphs. So this is this AE is the probability of one hyperedge to exist, right? So before you had a link between two nodes, now this depends on this E that is a subset of some nodes. And the probability of this to exist is a Bernoulli random variable that scales with a parameter that it's the sum of the pairwise Bernoullis that you have between these edges. So this is may not be immediate, but the idea is that you have each node in the potential hyperedge that has a probability of all these nodes have a probability of interacting with each other. You take the aggregate contribution of all these probabilities. That is exactly the sum that you find here. So Ci is the class of node I, Cj is the class of node A. You sum them all together, and you sample the probability of a certain hyperedge to exist. I hope this can settle a bit.
It's the mean.
No, this is just a normalization factor. It's not exactly the mean. It's a normalization factor that also allows us to control the sparsity of the random graph, of the hypergraph. Sorry, because fundamentally you don't want it to be too dense. Otherwise, message passing has problems with convergence, and it's a flaw of message passing, at least in its basic configuration. So yeah, that K is just a normalization factor, but it's not exactly the mean. Okay, and now once you build this hypergraph, so you have this generative model, you detect communities, and here there is a red dot, so you need to be careful here, because this is where the hard bit comes. So, but I'm not going to show you the hard bit. So again, what we know till now is that message passing is a method to perform inference on graphical models. So this, as I told you, these are just mathematical structures that allow you to compute the probabilities that each node belongs to a class. Great. And now we want to hone a bit the intuition on what message passing actually is. So message passing gives the node of, let's think about graphs, let's say here, of the probability of a node I, let's say this node here, to belong in a certain community. And it's based on the neighbors. So it's fundamentally a set of equations that gets iterated, so it's just what it is in practice. And the probability of this node here to belong to a class is depends, because of the formulation of these equations, only on its neighbors here. And the idea is that you have this set of equations, you iterate these equations, and then you get the marginal probabilities of each node to belong to a class. I don't want to go too much into the details, but this is just the intuition of message passing. And because message passing is formulated so the probability of each node depends only on the probability of the neighbors. Because of this, it's only exact on trees, and that goes back to the sparsity question. So you want it works best, or it works well on sparse networks or sparse hypergraphs. Okay, so this is and this neighbors is the node that have, so it's not really a neighbor, but we're gonna think about it. Okay, this though brings on a challenge that there is additional exponential complexity. Because in a network, you're lucky because you have, in general, you have the number of neighbors of a node depends on the degree of the node. But here you have that nodes can potentially belong to very large hyperedges. So a hyperedge, so it's a set that potentially can have all the nodes of the graph. So potentially a node could be adjacent, could be communicating in a group interaction with all the nodes of the graph. So
Is this really just exponential complexity? That sounds actually too good to be true.
it is
It's only exponential.
It's exponential, so it scales as a number of community to the dimension of the hyperedge. So for each hyperedge, you have exponential complexity.
So if you have the hyperedge is bounded in size.
Exactly. So
Yeah.
This would work well if your hyperedges were small.
Yeah.
And this is exactly actually what I want to point out. So that most of the literature now on hyperedge, on hypergraphs has a flaw, at least in my opinion, that stops at an approach. So many of the methods, they tend to be very nice, but then they work theoretically, but they work well in practice when you run the code with your hyperedges can take 2 nodes or 3 nodes, right? But then if you look at like social media data, or if you take data from WhatsApp and from group chats, now the amount of people that can be in a group chat in WhatsApp, I think is scale of hundreds or something. So of course your method will not allow you to, will not run for hyperedges that are very large. But we found a solution. Kudos to my collaborator Nick, present at the end. So you can solve this with dynamic programming. So you can split up a bit the message passing iteration and find a recursive relation in the updates of these equations. And this unburdens the complexity from exponential to polynomial, and it was really, when we figured it out, we were very happy. Okay. So this is how you do it. So you can perform community detection, and now the question is what happens to the phase transition, and this is what happens. So what you see here is the same setup you had before, right? So you control the in degree and the out degree now of the hypergraphs, and here you have a more assorted structure. So the mathematicians talk mainly to mathematicians and less to the others, and here you have the mixed up case. And here you see the phase transition it's exactly what you found, what you had before. So this is for dimension 2, so it's the network case. And this is the hypergraphs case. So in the model that I defined before, so in the planted model that I gave you before, where the graph is sampled with the rule that I gave you before, you find actually that having larger group interactions can help you recover more efficiently your communities. So this phase transition shifts to the right. You can recover for more mixed up hypergraph community. So it seems that group information actually helps you in this case. Okay, again, if there are questions.
So about this property,
This one
is a zero.
here. I think this is just a numerical issue. I need to think about it, to be honest. It can be either a numerical issue or related actually to the assortativity. I cannot answer right now. I'm going to think about it. So maybe I can think about it and tell you later. So here you have a. Yeah, no, of course. I think it's because, because here you have an assortative structure, but here you're actually in the case where the communities are isolated. So when they're isolated, actually, I think you need the thing that this happened because you need to have some. So imagine you have the two partitions are very isolated, and in order to, and in this case, they will not share any information. So what happens is some sort of random assignment in the two communities. Or like message passing will run separately for the two blocks of your graph. Once you start building some connections, some information gets shared between one community to the other. And so the community detection actually works. So in this case, it's like running message passing separately for the two subgraphs.
So because you don't know anything about the others, you can
Exactly.
identify the community.
Exactly. So that's why it happens. It's not numerical. Yeah, that's the reason. Yeah. Give me a second. Okay. And the question then was, can we recover the phase transition critical point in closed form? Yes, we can. The expression again does not really matter. What matters is that this is going to depend on some certain properties, that certain features of the graph, like the number of communities and the degree of the nodes, so that we had also in the graph case. But also it depends on how the hypergraphs of the hyperedges look. So it has some what's called higher order information. So the phase transition, of course, shifts if you have hyperedges of different dimension. Okay, I'm gonna go back to this in a second. So now the third question is, does the results tell us something about hypergraphs? And this is I think, a very interesting result that formalizes a bit an intuition that it's quite spread into the literature. So again, so I started saying one thing, to convince you one thing, that hypergraphs and graphs are different objects, and this is true. So now let's try to understand, to quantify this intuition. So the common intuition that you have in a lot of the literature in network science, and particularly hypergraphs, is that hypergraphs are more informative than graphs. So there is this higher order information, but what is exactly this higher order information? What does it mean in practical terms? And we try to quantify this. So so again, we had this phase transition that happens at a critical point based on a certain function f. What's nice about this is that from this function f, that tells you exactly where this phase transition happens, you can isolate a function g. So you can disentangle the graph contribution and the contribution that depends on the hyperedges. So it's actually a product. You can define a function g that depends only on the hyperedges. So this is exactly the function that tells you how much this phase transition shifts based on the fact that hyperedges exist. So not any other network property, not the degree, not the communities, but because of the hyperedges. This function, this is important. So the lower this function, the better. This is just the way you can take literally the inverse of this function, and it will work the other way around. But this is the convenient way we define it. So this is just a reminder there that can be useful. And then this is a bit a tricky bit. So this is why the slide is there. And then you introduce free quantities. Okay, let's be careful here. So you have this probability. There is the joint probability of sampling a hyperedge among capital E hyperedges. And then within each hyperedge, you have a binomial coefficient. It would be the probability of sampling if your hyperedge E has a size that is modulo E. Then you would have a binomial coefficient modulo E over two edges that you can sample, right? So if you have this hyperedge, then you can sample this pair, this pair, this pair. And so this would be the probability of sampling a hyperedge, and then independently a connection within an hyperedge. This is simply a uniform draw over the hyperedges, and this is the probability of the click. So to go back to the first question that I got, I think this is though a weighted click. So what happens here? You're gonna switch. Oops, sorry. Yeah, this is correct. So because you have an overlap of two hyperedges here, this weighted click will weight this edge here twice, right? So this is the independent margin. So it's a joint margin where the sampling of the hyperedge and the sampling of the edge happens independently. Here you have a graph, and from the graph you build a click that is a weighted network where the probability of this edge to appear is weighted 2 because there is an overlap. Okay. So if someone has questions, this is a good moment, I think, because the next formula is a bit, it's interesting. So it turns out that once you define these quantities, this function g that tells you where the phase transition happens again, so where the system becomes more detectable, it is actually this. So it's the conditional entropy of drawing a pair of so an edge given the hyperedge. So the conditional entropy, so, okay, what does this mean? It means that imagine you have a graph. If this graph holds a lot of information about the click decomposition, so about the network you can build with, then this conditional entropy is lower. So the conditional entropy is the amount of channel information you need to recover this variable knowing this random variable. Okay, so let's try to 1 second so to explain it with the simplest example. So this conditional entropy is equal to 0, where if you know a hyperedge, you will know an edge. So given all the hyperedges, you are deterministically able to recover the click decomposition. And this happens if your hyperedges are simply the edges. So in the case you have a hypergraph, and then you want to recover the click decomposition, you know that you're going to be able to do it deterministically. The hyperedges don't exist. So they're simply equal. The more these hyperedges overlap, so the more you have information about your click decomposition, weighted information about the click decomposition, the more you're going to be able to recover information about the click. So that is to say, all of this, going back to community detection, that maybe is the key message I want to tell here, is that community detection becomes easier when this is lower. So community detection becomes easier when you have a lot of overlap between hyperedges. That's the key information that we want to
So, sorry, does this end at the clock?
Yes.
Okay.
Okay. So just to and this is simple rewriting, simple to say, but from this you can simply rewrite the conditional entropy of a random variable like this. So this is the total entropy of the random variable sampling and edge, and this is the Ka and divergence between this three and this, and the mutual information between this. So the formula is not important, but what do I want to say with this? This is another interesting take and a bit of a difficult take on the problem, but it's kind of interesting. So you can also reformulate the problem like this. So given a certain click decomposition, given a certain graph, and given a certain number of hyperedges, can you go from the click decomposition to, as I said, to a click decomposition, there are many hypergraphs. So there is one special hypergraph, though. There is the one that's going to give you more information about community detection, and it's going to be the hypergraph that yields the lower value of G. And this graph is going to be the one with the highest edge overlap, hyperedge overlap. So this problem is interesting. Again, I don't want to spend more time than this on this slide. You can ask me about this later. It's a different rephrasing of the problem. But this is interesting for a reason, and this is the message here, that what happens that in practice, it's hard to actually record group interactions experimentally, and sometimes your hyperedge data set are rather incomplete. So you don't have a group interaction, you have single interaction. Some people are interested in given a certain network, given a certain graph, recover the hypergraph. So say, we observe that people interact pairwise. Can we say something about their group interaction? Well, in general, you have plenty of hypergraphs you can build, but there is one special graph. There is the one that is going to give you the highest detectability, and you can recover it through this one right here. Okay. And okay, the last slide, and then I'm going to conclude, is this. So all of this is nice and works well in theory, but it also works well in practice. And this was also another interesting result. So all the examples that I discussed here, I wanted to be a bit more technical on the results of the work. But what's nice is that you can also recover communities better when you include groups interaction. So this is a data set where there are high school students. They were a trackable device that it was a sort of proximity sensor, I believe, that registered when these two students interact. And so these are the classes at school that they attend together, that they belong to. And then this is when you run message passing, only including pairwise interaction between the students. You see that you cover these two classes. And if you include also free, the hyperregister dimension free, so free-ways interaction, you recover a bit more of a denser structure in the communities, and this keeps improving actually when you include hyperregister of dimension 4. So yeah, okay. So this is it. I'm going to leave with one message. I said it plenty of times, so there were many messages, but okay, you can cancel everything now and remember one thing. So because all the other take-home messages, I think, were rather technical. This is maybe more motivational. And it's something that I believe that, so principle, maybe in this constant variation, principle meaning variation, and efficient meaning non-exponential. Inference, so detection of communities in large complex systems is possible. It just takes effort. And I think the morally right thing to do is to do it. Okay, so again, this is the paper. And then, yeah, I want to also thank Nick and Katerina. Yeah, they were great. And I mean, most of the merit for this work goes to them. And that's it. Thank you.